Okay, so we're going to graph this function. Should have been moving these around. Okay, we're going to graph this function. I hope that through all our talking about graphing, you're really, and we're going to talk about it some more today, and it's really, coming home for you what a graph is. When we graph things, it means something, and the connection to the equation should be clear to you. So when we take an equation and we graph it, the connection between the two things should be really clear. All right. But for now, I'm going to say we discussed this in class, what all of these things mean, right? And I'll give you like a really quick refresher here. So we started out with y equals the absolute value of x, and we found that it looks like this, something like that, right? This side has a slope of positive 1 for every 1 that it goes over. It goes up 1, and it steps up like that, right? Slope. This one has the opposite slope, not opposite reciprocal, because that would be perpendicular, all the time. This one happens to be perpendicular, but this one's just a negative slope. So it goes for every 1 that goes up, it goes to the left one instead of to the right one. Okay, and it's a mirror image of the right side. Okay, so then we took y equals the absolute value of x, and let's just look at that part of it right now. We subtracted 6. But this function is exactly the same. If we cover this up, it's exactly the same as that function, right? Except for what? Yeah?
Move down 6 on the y-axis.
The graph is that, yeah? But the function, this as an equation, it has the exact same outputs as that function. So this one has the exact same outputs as this function, except for we subtract 6 from every output that this makes. Does that make sense? It's exactly like this function, we subtract 6 from every output. Okay, well that would just make every number 6 less, every output 6 less, and if we look at the graph, that would have the effect of, since output is vertical, y is vertical, and we're making every output 6 less, it would move it down 6. So that would move it down 6. And then we looked at something like this, 2 times the absolute value of x. This function also almost identical to this function in its outputs, except for if we ignore it, they're exactly the same. But this one takes every output that this makes and multiplies it by 2. Okay? So every output gets multiplied by 2. If we look at the graph, what effect did that have on the graph as we compare it to this graph here? Michael?
Makes the line steeper.
Makes both of the lines steeper, right? Because instead of going to 1 and going up to 1, you go over to 1, you go up to 2, because 1 just got multiplied by 2. The output of 1 just got multiplied by 2. This one, you go over to 2 and you go up to 2. That's the point on this graph. But this one, you multiply that 2 by 4. So you go to 2, and then you would get 2, but you multiply, or not multiply it by 4, multiply it by 2. You multiply this 2 by 2, and you get 4. And then you multiply this 3 by 2, and you get 6. Like it's still straight, still a straight line, but it's steeper. Okay, so this is twice as steep when we look at the graph of it. If we look at the equation, then we'd say the outputs of this function are twice as big as the outputs of this function. If we look at the graph, we would say it has affected the steepness of the graph. Then we looked at the absolute value of x plus 1, except in this class, we didn't quite get there. Right? We didn't quite discuss adding stuff and subtracting stuff inside the parentheses. But again, if we were to ignore this, it's exactly the same as that function, the absolute value of x. Except it is a little bit different than these guys, because these ones took the output of this function and changed it. Subtracted 6, multiplied by 2. We could multiply by a negative, right? That could be a different variant on that. But this one doesn't do it outside the absolute value. It does it before you take the absolute value. Right? And to kind of find the center of the graph again, you need to put numbers that are into x that are 1 less than the ones that you were putting in here. Right? If you want to find the center of it again. If you want to find that center line, that line of symmetry, you would have to back up. X would have to be -1, so that when you add 1, the inside is 0. Right? The inside was 0 here, at 0, you just plug 0 in. But to get this to be 0, you have to plug in a -1. So now all of our x values are back 1, to the left 1. Right? So this shifted the graph left 1. And if we subtract it, it would move it to the right 1. So if we put all those together, then we have everything that happens to this graph. We can move it down 6 and to the left 1, put a point right there. So what I just did is I moved from the origin down 6 and to the left 1. So I must have moved that point that's at the origin down 6 and to the left 1. Did we talk about what that point is called? That pointy point right there? No? Okay, starts with a V. The vertex. And vertex is just a word that could be applied to other contexts. It's like the pinnacle, the very top, or the very bottom, that pointy thing. Right, so we just move the vertex down 6 and to the left 1. So we can like check, check, and then we need to make sure it's twice as steep. Right. So this one goes over 1, up 1. This one should go over 1 and be twice as steep, so it should go up 2 for every one that it goes over. Over 1 and up 2, over 1 and up 2. And we could just mirror it there, and there it is. Questions? You're getting what?
I'm just getting like a funny line. I'm not getting a V.
How, did you put in -2, you said? Okay, -2, we should be seeing something else. Let's see what happens. X, Y, -2, okay. So we put -2 in here. -2 plus 1, -1, okay. Then we take the absolute value of -1. What's the absolute value of -1? 1. 2 times positive 1 is 2. Minus 6 should give us -4. So if this line comes down and comes all the way down to -6, but then when we step over to -2, because we take the absolute value of that number, we turn a positive. Now we just start doing the same thing that this side does, but just in this direction. Okay. That's what I'm guessing happened. Did that help, Misty? Okay. And if you don't know how, again, if you don't know how to graph something, if you don't know how a function's graph is supposed to look, plug in some points. Plug in points and plot them and draw what the shape looks like it's starting to look like. And if we were here all day long and we just kept putting in numbers 0, -1, -0.5, -3/4, -1/4, just plugging in all these values and we plotted all these points, that's all we would wind up doing is drawing this line. But at some point, you suspect you've got the idea, you've got a notion of what it's supposed to look like, and you just go ahead and draw that line rather than drawing all those points. That's what it's all about. Okay, so here we have, here we had an equation, we turned it into a graph, and we're going to turn a graph into an equation. So how does this graph look compared to this graph? Less steep, excellent. How much less steep? 3 less steep? 3 times less steep?
Yeah.
Okay. And so, a third as steep? Different ways to say it? Yeah, a third as steep. So, what of these numbers affected the steepness here?
2.
The 2 affected the steepness, making it more steep, right? Making every output twice as big. We want to make every output 1/3 as big, right? The absolute value of x looks like this. And this output is 1, this output is 2, this output is 3, and this is helpful because there's a point right there, it's right on the lines. So you see this output is 3. How do we take the output of 3, multiply by something, and get 1? By 1/3, multiply by 1/3. So if we multiply every output by 1/3, then every output will be a third as high as the outputs from this function here. I should change the color of this so that it's a little more clear. All right, so we have to graph this piecewise function. I'm going to take a crack at it. I have 2x plus 1 there. Right? That's a graph I know how to make. It's a line. It's got a y-intercept of 1. I'll put a point right there. And it's got a slope of 2, so we'll go up 2 and over 1. And I know now that I can connect the dots and make a line. Okay. How does that seem? Does that seem good? Is that what I should do? Is that how that works? Maybe after that, I move on to this other one. Right? It's also got a y-intercept of 1. I'll put a point right there. And a slope of negative 1, so up 1 and to the left 1. And draw that. And all good?
Can you repeat what you just said? Like, how did you go up one and then?
Up 1 in there.
Yeah, and then, but like, how did you like start off like with the positive one on the left?
Here.
Yeah.
Because that's the y-intercept of this line.
Okay, cool.
Is that right? Is that good? That's it? We're done?
Wait,
There's something wrong.
which one?
What are we waiting on? Sorry.
Search about 50 lines there.
Are there? One thing, just to pique our curiosity. First of all, this is a piecewise defined function. Okay, what about a function? What's a function? What's special about a function? It's a little sentence that every function has to meet. That condition every function has to meet. What is that condition? Yeah? So every input has exactly one output. Let's see. Let's go to this input. Right? What's the output for this input?
There's 2.
There's 2 of them. There's this one and there's this one. If I drew a vertical line through there, I would hit both of those places, right? Therefore confirming that there are 2 outputs for that input. That can't be right. So that at least tells me something's up. Because it's a function. It says it's a function, but it's the way I've drawn it, it's not a function. But I drew those 2 graphs, right? What's wrong with that? Maybe do some jumping jacks? You guys some jumping jacks? Is that what you need? Yeah. Stand on your heads. Shake each other by the shoulders. Why don't you just grab the shoulders of the person behind you and in front of you and just shake each other. Just wake each other up. Okay, so what's up with this? What's wrong with this? It's obviously not a function. What did we do wrong? It's my fault. What did I do wrong? Okay, I won't put the blame on you. What did I do wrong?
Drew too many lines.
Okay. Too many lines. Should I just erase them both?
Well,
Should I just erase the red one or just erase the orange one?
Erase the bottom one.
There's a red and an orange one.
Erase the bottom.
I thought they were all red.
Oh, sorry. Maybe I should use colors that aren't so close to each other. Do what? Erase something?
No.
Erase what?
All the lines under positive one on the y-axis.
Erase all that? Oh. Under positive one? That's what you said. Under positive 1 on the y-axis?
No.
Those
2 lines.
What?
Oh, that's what I mean. Like, erase that and erase
Yeah.
that?
Why not?
Well, 'cause it's wrong. Because that's... What made you want to do that?
Because I've never seen them like that.
Maybe you want to do that because it looks like that? It looks like an absolute value?
Mhm.
Well, I mean, that would give us the warm fuzzies and all. But we have to look at how this function's defined, right? Am I supposed to graph this function?
No.
Answer is yes.
Yes.
Okay, I am supposed to graph it, but with some restrictions. Michael?
Well, aren't you supposed to like stop the lines at 0?
Why?
Because the inequalities,
Because of these things.
yeah.
Okay, so see what it's saying. And as we move on, this word if will disappear. It'll be understood that's if, okay? So, but it's here right now. It's there. It's really there. So 2x plus 1. Graph that. Do it. Do graph that. If you're at an x that is greater than or equal to 0. Right? So that one was the orange one. That was the orange one.
You like
Red.
That orange is here with the red.
All right. I'll make that blue. I'll make this one blue. Make this point blue. Okay. Fair enough.
That's good.
That's orange. That's dumb. Ooh. Tortured life. All right, so now it's blue. Now we have orange and blue. What's orange and blue? Pepperdine is orange and blue. What else is orange and blue? Broncos. Okay, so this is the Broncos function. So we graph this orange one only if x is greater than or equal to 0. Where is x greater than 0?
At the 1.
At the 1?
On the y-axis.
That's a little bit confusing. Let's just say, on a graph, where is x greater than 0? To the right. Right? Not to the up and not to the down, not to the left, but to the right of the y-axis, this direction, x is greater than 0. So what? Now we finally figured out where x is greater than 0. So what am I supposed to do when x is greater than or equal to 0? What am I supposed to do? What is this telling me to do when x is greater than 0?
Oh, use the top.
Use that orange one, right? Use 2x plus 1 when x is greater than 0 and when x is equal to 0. So not when x is less than 0. So I've drawn too much. Let's not use this. Everything to the left, right? Everything to the left, I should not be using this orange one. So I'll get rid of that. Goodbye. What's that? Are you confused?
I'm just frustrated.
About what?
I'm with Mickey on this one.
Everything.
Everything? You're mad about everything? Okay. I guess good luck.
Thank you.
Unless,
I will need it.
unless you have, some words. Some more words.
No.
Appropriate words.
Move on.
Okay, moving on. Well, how about this blue one? Am I supposed to draw this blue one all the way across every value of x? What values of x am I supposed to use it for?
Less than 0.
For less than 0. Where is x less than 0?
To the left.
To the left. Okay? So, to the left of the y-axis, I should be using this function. So let's get rid of this. So why was Mickey wrong? She was wrong. Why was she wrong?
She didn't know why.
Well, that's one big thing. But you said to erase everything that what? Was below, right? It's not about below and above. It looks like it could be. Like if we were just like on a construction site and we wanted to get this thing done and you said, hey, just erase everything that's below that dot right there where they meet, like it would look the same. But we do want to understand why we get that, how we arrive at that shape, okay? And the reason why is because this function is only supposed to be used over here, right, when x is less than 0. That's a left and right thing, not an up and down thing. And this function is only supposed to be used when you're greater than 0, when x is greater than 0, or when x is equal to 0. So really, like the inside of this dot should be orange. Right? like an open circle for the blue one, because we're not supposed to use the blue function when x is 0. But we do use the orange function when when x is 0. Okay? So the filled in part where we're at 0, that's the responsibility of the orange function, the top function. And otherwise, at any value other than 0 in the negative direction, that's going to be the blue function. Sorry if you felt like you felt like I was picking up. Did it feel good? Was I picking up?
Mm-hmm.
Oh, I'm sorry. I didn't mean to. I thought we had a banter. You don't have banter yet? Yeah? No. Banter?
What?
You know what banter is? Like, you just joking around with somebody and you throw out stuff back and forth. Yeah?
You could have told me.
Next time I'll be like, I'm about to banter. Ready? You're wrong.
That would be a lot better.
Okay. Smiling? I thought smiling was good. Questions from the quiz or off of the quiz, some other part of the homework? Michael?
Can you go over 30?
30. 30. Yeah, I can do 30.
We have book work too.
If you did a test that you
Did she do? Oh yeah, she did.
did you have a test that you yesterday?
We have a packet.
Oh, yeah, I did.
Yeah.
Just read it. There's like all these numbers.
I'm probably wrong. Yeah, I didn't know you had to
Are we have
Okay,
I'm gonna.
so we're supposed to describe the error here in graphing the absolute value of x plus 3.
I have
Absolute value of x plus 3.
Oh, just kidding. I get it now.
Why?
I don't.
How is that wrong?
Well, because they went up on the y-axis 3,
Yeah.
which means it would have been like line x line plus 3 on the outside.
This is the graph of y equals the absolute value of x after you take the absolute value, then add 3.
Yeah.
Yeah?
So you'd have to go to the left on the x-axis 3 to get that graph.
To get this graph, yeah, we'd have to go to the left 3. So, so this graph would be moved to the left 3. Just like that, I would have to run right into that graph. So to the left rather than up 3. Another question?
Let's go to that extra section.
Yeah,
number
that
1.
extension, I did
That
not understand
extension.
any of it.
Okay.
Number 7?
I heard 20.
I was so lost.
Oh boy, you hit on one of my least favorite phrases. I was so lost. I was so confused. I had no idea. Okay? I'm not denying that you may feel that way, but I mean, what does it do when you come here to tell me that, or to tell anybody that?
Well, I
Like,
went on YouTube.
if you went to the,
sample problems, and 2.7 wasn't on there for sample problems.
well, I appreciate you doing that. That makes sense. They didn't do it last year. They changed the statement. So thank you for letting me know that. I'll fix that. But if you went to the mechanic and you gave him your car and you're like, my car is so broken. What is it gonna do? Then he's gonna say, great. What's wrong with it? You know, like what was the problem? What's the sound it's making? What are the symptoms of your issue here? Right? That's what I want. I want usable information about your being lost. If you have no idea, it means you paid no attention in class because we did talk about it. Okay? We did talk about it. You gotta have some smidge of an idea. Okay? If you didn't, you could go back and watch the videos from the lectures because those are up every day. Okay, so just that's my thing. After years of teaching, I've come to realize that really gets my goat. Yes?
I just don't understand like the F-4 part. What do you do with that?
In the extension,
Yeah.
we'll get there. I had Carl asked for number 20 in just the regular, so we'll look at that one real quick. 20, the rough sketch of this. That. There. Okay, so we're supposed to write the equation for this graph. We could start there. That's for sure going to happen. What kind of a function is this? That's with an A. Absolute value. It's an absolute value. So we should put some absolute value signs there. Right? There's definitely going to be an x there. There might be something in there with x. There might not be. Well, what can we say about this graph compared to, again, we're talking about compared to this graph. So, how is this graph compared to that graph? What's something that happened to this graph to get to this graph? Steeper. Okay, how much steeper? 2 times as steep. This one goes up 1 and over 1, up 1 over 1. This one goes up 2 and over 1. If you look at your books, you can see that it's got a nice grid there. You can count that off easily. So that next point is up 2 and over 1. So it's twice as steep. So what do we do with that? Where does that go? Multiply it by 2. Multiply the absolute value by 2. Right? Because once we take the absolute value, right, this is what it looks like if you just take the absolute value of x. If you take the absolute value of x and then multiply by 2, all those outputs are going to be 2 times as big. So that function is going to step up twice as much for every time you move over. Okay, what's something else? It's steeper. What else?
Farther over.
Farther over. How much over?
5.
And over which way? Okay, so it's moved over 5. We just talked about this over with this one. X plus 3, what did that do? It moved it to the left 3.
Minus 5.
So minus 5. That moves it to the right 5.
Why is it minus when you go to the right and then positive when you go left? You have to bring it back.
Let's see.
I have no idea. I'm trying to explain this, it's not working. Sorry, that's okay.
Well, either way, it's still positive, it's the absolute value.
Well, true. But still trying to think of the best way to explain it. So let's look at y equals the absolute value of x. The graph looks like this. A really useful place on the graph to look is right here. Okay? And I'm not putting a point at the origin necessarily, I'm putting it on the vertex of this shape. So what would this look like? Well, we'll do minus 5. So what this is doing is before you ever take the absolute value, you take 5 away from the thing that you're going to take the absolute value of. Okay? Good? Okay. So let's figure out where this vertex would be for this graph. Okay. Well, this vertex is going to happen, it's right in the middle. Okay? Let's also think, it's like the smallest output you could possibly get from the absolute value function. Right? Here's some bigger values you can get. You can get 6 out of this function. You can get 5 out of this function. You can get 1 out of this function. What's the smallest value you can get out of this function right here? You can get 0 out of it, right? You get 0. That's the very bottom. That's where the vertex is, the very bottom of this thing. Okay. So how do you get 0 to come out of this function? Yeah, Michael?
Put 0 in.
Okay. And we'll be more specific. The thing inside of the absolute value has to be 0. Right? And in this function, it's easy enough. You put 0 in there. But what do we have to put in for x in order for the inside of the absolute value to be 0 and therefore to find where the vertex is?
5.
You got to put in 5. You got to put in positive 5. to find the vertex again. For 0 to be inside the absolute value, and so when you take the absolute value, you get like the very bottom of the absolute value graph. So you have to, like, to find your center again, to find that vertex, the middle of that graph, you have to go over to +5. And then from there, it looks the same as that graph over there. You move to the right 1 to 6. 6 minus 5 is 1. You take the absolute value of 1, and you go over 1 and up 1. And to the left, 4 minus 5 would be -1, right? So we're getting the same, we're taking the same things, taking the absolute value of the same things as we are over here when we go to the right, 1 and 2 and 3. Okay? But here, to get 1 and 2 and 3, we have to put in 6 and 7 and 8 because we're subtracting 5 from that number. So the numbers that we put in for x have to be 5 bigger to compensate for 5 being taken away from them. Okay? Does that help at all? I know that if you just look at the signs, it's weird and it's counterintuitive. But if you do look at it that way, it does start to make some sense. So it does, we do need to subtract 5 to move it to the right 5. And anything else that's happened to this graph?
It went up 2.
It went up 2. How do we make it go up 2?
Add 2.
We add 2. Before we add 2, it's still down here on the x-axis. But then when we add 2, and we add 2, we add 2, all the points, we add 2 to them, they all come up 2. So we subtract 5, that makes it so that we have to start at x is 5. We multiply by 2, that makes it twice as steep, and then it moves up 2. That help? Okay. Should we move on to the extension?
Yes. Yeah.
Okay. Now, there is absolutely no way that you should have no idea because we just went over one of these, okay? We just did it. Right? And if you're confused about something else, that's fine. Maybe you're confused about the f with the -4 thing, that, you know, you need a little reminder of that, that's fine. Don't tell me you have no idea because we at least just did it. And if you have questions about that, you didn't understand a part of that, then I'd be glad to explain it. But if we go from here, okay, we're talking about number 1. Number 1, to do number 1, you have to refer to that function that's sitting up there. And that function is this piecewise defined function, f of x. Is defined by several different functions, 2 of them. 9x minus 4 if x is greater than 3. 1/2 x plus 1 if x is less than or equal to 3. I'm sure that's what it said. To just remind you what that f with parentheses -4 means. Just remind you about what function notation is. So let's look at a real simple function. F of x equals x plus 2. Now remember, this is function notation. This is not f times x. It's a function named f, and x is the input. Function named f, and x is the input. So if you say f of -4, what does that mean? Michael?
Everywhere there's an x, plug in negative.
Wherever there's an x, you put in -4, right? So this goes in there, and wherever there might be an x, there might be several x's. But here it's simple. You just put -4 in there. So that's -4 plus 2, that's -2. Right? F of -4, this is read f of -4, not f times -4, nothing else except for f of -4. Right? That's all it means, that's all f of -4 means. It means plug it in. Okay? So the thing that adds a little bit of a challenge, if you want to call it a challenge, is, okay, so if I know this, it means I'm supposed to plug -4 into the function, right? Which one? That's the question here. Which function should it go into?
Bottom,
Why?
because it's less than 3.
less than 3. Negative 4 is the number that's x, right? It's supposed to go in for x. It's less than 3. It's not greater than 3. It's less than 3. So this is the function we should use to plug it in. Okay? So 1/2 times negative 4 plus 1. Negative 4 times 1/2 is negative 2 plus 1, negative 1. Just plug it in, and when it's a piecewise function, you just have to decide which function it's supposed to go into. And there could be 2 functions or 3 functions or 4 functions, but there's not going to be any overlap of the x's, right? If you were going to write a piecewise function, you want to keep it clear. You do not want to have, like we wouldn't have x is greater than 3 and x is less than or equal to 4, right? There would be overlap in those 2 intervals, and there would be confusion. If I have 3.5, that's between 3 and 4, and both of those cover that value. So there's always going to be a perfect line cut between this and whatever else we might use. How was that? Is that helpful? Did that clear that part up? All right. Are there questions on other parts of it? 7. Okay. 7 h of x equal to 3, 1, or 5, depending on if x is between 0 and 2, so I should use that. But 2 is less than x, or sorry, 0 is less than x, and x is less than 2. Okay. Oh, less than or equal to 2. It's 1 if 2 is less than x, or x is less than or equal to 4. And it's 5 if 4 is less than x, and x is less than or equal to 6. We're supposed to graph the function. Okay, let's create a table of values first. Let's say I want to plug 0 in for x. Which function am I supposed to use? Anybody disagree or agree with that? Who agrees that we should put it in the top one? Raise your hands, usually signifies that you agree. Okay. You disagree? Raise your hand. Michael? Why do you disagree, Michael? You don't know? Well, I want x to be 0. I want it to be equal to 0. What does this say? X would be greater than, right? It's on the larger side. Greater than 0, not equal to 0. So where do we put 0? We what? Can't. There. What we would say is 0 is not in the domain of this function. It's not a valid input. Okay, so it was a trick question. All right, so let's do 1, 2, 3, 4, 5, 6. Like that. Okay, we want x to be 1. Which function should we use? The top one, because x is 1, and 1 is between 0 and 2. Okay, so we should put it into the function. So we put it into this function. What do we get out? 3. Right? What that's saying is your output is always 3, no matter what x is. There's no place to put x. There's no way for x to change the value of the output. It's always just going to be 3. Okay. Where should we put 2? Which function should we put 2 into? The top one still. If we're equal to 2, we use this function, and we get 3 again. 3, put it into the second one, right? Because it's between 2 and 4. And what do we get?
3.
1. Yeah. The middle one is a 1. And when x is 4, there's the middle one, and we get what? 1. And 5, we get 5, because now we're going to move down to here. It's between 4 and 6. Get an output of 5. And at 6, right? That's okay. We can put that in. It's equal to 6. Okay. What about 1.5?
3.
You get 3. How about 3.7? You get 1, because 3.7 is between 2 and 4. Right? So for all of the values from 0 to 2, I'm going to be getting out 3. So if we look at the graph, put a little divider here, 1, 2. So from 0 to 2, everywhere in between here except at 0, not at 0, because we can't have x be equal to 0. But everywhere in between and up to 2, we get an output of 3. Output is 3. Whether the input is 1, we get 3, or it's 2, we get 3, or it's 1.5, we get 3, or it's 2 3/4, we get 3. Right? So we get this horizontal line. But when we get to 0, what should we do? Put an open circle. We like to just do nothing, but doing nothing, it's not big enough. It's not noticeable enough. So we make it noticeable by putting an open circle, letting us know that once you get to 0, don't get to 0. Just stop before you get to 0. Okay. Then, when we move over and we're bigger than 2, but less than 4, or equal to 4, and we use this other function. And this function gives us out 1. Out 1. So from here, not including 2, because 2 is included in the other function, and all the way up to here, we keep getting an output of 1, and including when we get to 4. And then from 4, bigger than 4, up to 6, we're going to get out of 5. So 3, 4, 5. We get outputs of 5 for all those, up to and including 6. And these dotted lines, they're dotted because they're kind of imaginary. They're not really part of the graph. You don't have to draw them. They are helpful. Helpful guidelines. Okay. Gonna call it on this one. Gonna call it good. Gonna pass it on. Alright, it's time to graph some inequalities, which is an idea we're not unfamiliar with. We've done that before. So to refresh our minds, let's do some simple, very simple inequalities with just one variable. Remind ourselves what that looks like. X is greater than or equal to 3. I also want you to do a second one. X is less than 5. Shouldn't take long. Got our notes out. You graph those two. I'll see how you're doing. Talk about it about 45 seconds. Okay, so not surprisingly, many of you did just fine. If you want to represent this with a picture, all we need to do is somehow convey that 3 is greater than or equal to 3. X is greater than or equal to 3. So show all of the values for which that's true. So we should probably show where 3 is. Put 0 here and 3 there. How do we show that X can be 3? Yeah?
A filled-in circle.
Fill-in circle at 3. And so X can be equal to 3, but X could also be bigger than 3. Like, could X be this number?
Yeah.
Sure. And this one?
Yep.
Could be this one.
Yep.
This one. Right? How long can I do this?
Forever.
Forever. And what do I wind up with? This shaded in region. Okay? That shaded in region is kind of like a bunch of points that you drew so many of them, they all got mushed together into a shaded region. Okay. Oh, 1, 5, 0, 5. Can X be 5?
No.
How do I show that it can't be 5? Open
Open
circle, right? But I do want to get close to 5. I just don't want to get to 5. That's why we put an open circle. Well, can X be this?
Yeah.
Can be this? Can be this? Can be this? Can be this? Can be anything there, and so we wind up just mushing all those points together and getting this slightly thicker line, this shaded in region. Okay, let's do a couple more. We'll just say y. Y is greater than or equal to -2. And y is less than 9. those two. Should take about 17 seconds. I see most people doing the same thing, just drawing a horizontal line, and going to -2. Y can be equal to 2, and y can be equal to -2, or it can be greater. Here's 0, 9, and it can be less than 9, but not equal to 9. So we put that open circle and shade to the left. All right, and that's great. If you did that, it's just fine. It's exactly right. But something else we could do that would be exactly right is something that we're used to doing with y, and that would be thinking of it as a vertical component. Okay? So we can also do this greater than or less than thing in an up and down direction. Right? No difference. We could also do x in an up and down direction if we wanted to. We could make our number lines diagonal if we want. It doesn't really matter. But because horizontal and vertical are so accessible to us as human beings, we walk on horizontal ground, we look up and down at things. Okay, that's why we do it that way. So just a little note about that we could say things are greater than or less than by saying they're above a thing or they're below a thing. All right, so just little steps at a time. So another little step. We are going to be graphing inequalities, like one expression is not equal to this other expression. But for a while we'll be graphing this expression is equal to this expression, okay? Like this example. Y is equal to, this expression y is equal to this expression, -2x minus 1. We've graphed that several times. So that's what I want you to do. I want you to go ahead and graph that equality. And we'll talk about what it's graphed and not. Pretty good. And until I feel like everyone is fluent in graph and that like it's just getting old and we get it already, we understand it, we're fully fluent, then I'll stop saying stuff like this. But again, today I'm going to reiterate what a graph is. What it means. So I'll start this way. I'm just going to say something that I've said many times in a different way. So I'm taking the idea of letting y, since we're saying y is something, and I want to show it graphically, show it in a picture. Y is going to be something. If we let this be 0 right here, okay? So y is equal to a number, right? It's equal to a number. The thing is a number over there. Well, what should y be equal to? Should it be equal to? Could y be equal to 3? It can't be equal to 3. Y will never be 3. This is just a number line that represents what y is worth. Could y be 3? It could be 3. Could y be Could y be 5?
Mhm.
Yeah.
It could be. Could it be 0? Can y be 0? So y can be, what can y be? It could be any number. In this case, it could be any number. But if we were to just graph all of the numbers, like shade in this whole line, that wouldn't be very helpful, would it? Right? It would be true. Y can be all of these things. You could just shade the whole number line from negative infinity to positive infinity, and I told you what y can be. But it doesn't tell us the whole story, right? For one thing, y can't be two numbers at one time. That's kind of, so we're left to wonder, like, when is y 3 and when is y 5? Yeah?
Why don't you have an x-axis?
So that's the thing, right? If I'm going to say what y can be equal to, y can be all those things. But it's only equal to 3 when what? When x is something, let's say something, right? X has to be a certain number for y to have the value of 3. Right? Can anybody tell me what value x would have to be? Yeah?
-2.
So if x is -2, then y would be 3. Okay? So I can't just say y is 3 and y is 5 and y is 0 and y is all these things. Okay? That's why we have another axis. Okay? We have two things going on here, not just one. Y isn't just like given a range of numbers that it can be. It can be that range of numbers depending on what x is. So we draw the other axis. We give it some scale. Okay? And y is not just 3, y is 3 if x is -2. So if x is -2, then we go up and we say y is 3. Right? If x is -2, y is 3. That's what that point's telling us about that function, about that equation. When will x be negative, or when will y be worth -1?
When x is 0.
When x is 0. So what do we call that point right there on the y-axis?
Y-intercept.
Y-intercept. So that's a useful point to know. And when will y be worth 1? When will y be worth 1?
-1.
When x is -1. So if x is -1, then y can be 1. And I'll just get this out of the way. I'm about to draw a line. There. Because if I keep doing this, I keep plotting all these points. Again, just like we got that shaded area on the one-dimensional graph. These are one-dimensional graphs, left and right, the only dimension. Just like we got a shaded area there, what we wind up when we graph all those points is a line. They all merge together and they make this line. Great. So if I pick a point on this line, like this point, or this point, or this point, or this point, any point. If I pick a point on the line, what's so special about that point on the line, like compared to this point over here? So special about that point when it's right on that line, yeah?
It fits in the equation.
It fits in the equation. We take, well, explain that to us. In what way does it fit into the equation?
Well, if you plug like that point in, the equation will be balanced.
What's that? It makes the equation true. Yeah. Two very good math words. It's true, right? This is making a statement, and it's either true or false. If this side and this side are not balanced, as Michael said, then this would be false. It would be true. So that's the special thing about points on the line. A point is made up in this two-dimensional plane. It's made up of an x and a y. If we plug in that x and that y, and that point came from on the line, then we'll get a true equation. We get a true statement. And points that are not on the line will not make it true. Okay. So, and that's nothing new. I've said that lots of times. That's one of the things that I've said lots of times. That if you pick a point from on the graph that that equation makes, if you you pick a point from on it, you put the x and the y in there, it'll be true. Okay? So if we put, say, -2 in here and 3 in there, this will be 3. All this math will boil this down to also 3. Both sides will be equal to 3. But what if I pick a point down here, below it, right below it? So like -2, -2, -1. Will that make that statement true?
No.
No, it would not make that statement true. Because if they're not equal, then one side has to be what? If the two sides are not equal, one side has to be more or less, right? And if one side's more, the other side's less, right? So one side has to be more, and by default, the other one would have to be less. So here's the question I want to ask you. If one side has to be less, and one side has to be more, if we take this point and put it into this statement, it'll make it false, for one thing, right? It won't be equal. Which side will be less? Will this side be less, or will this side be less?
Why?
This side, why? How come?
Well, okay, no, I lied.
You lied?
Yeah.
Whatever you decide, have an explanation. What explanation do you have for deciding the y side is bigger or the y side is smaller? Okay. What's your reason?
Okay, so you plug -1 in for y, and then you plug -2 in for x,
Yeah.
and then -2 times -2 is 4,
Yeah.
minus 1 is 3, and you get -1 equals 3, and y would be less.
You'd have -1 equals 3, but it wouldn't be equals, this would be less,
Yeah.
right? Okay, so the y side is less than the side with x on it. Agreed? Okay, and that makes sense because, look, if you put -2 in for x, what do you get on this side?
3.
You get 3. That point on the line tells us that, right? So if I want, pay close attention to the question here. If I want y to be less, right? We're just talking about right in here where x is -2. If I want y to be less, where can I find points where the y side is going to be less? Yeah.
Below the line.
Below this point right here, right? This one will work, right? If x is still -2, then the y is going to be, well, because it's below that point, the y is going to be less. And here, and here, and here, right up to the line, here, everywhere down here, you could like shade this all in, just like we did with those other inequalities.
And you just shade everything below the line?
Yes, okay? Because for any x comma y on the line, what's going to happen when I plug this x and this y into this equation?
It's going to be equal.
Both sides will be balanced, both sides will be equal, it'll be a true statement. Okay? What happens if I pick points that are above this point?
Y will be more.
Y will be more than what you get on the x side, right? Because when you put in this x, you get this y right here. So if I pick y's that are above, bigger, then the y side will be bigger. If I pick points that are below, then the y will be less. Okay? Less. That'll work for any point on the line, all of them, right? There's an infinitely many. So if we went to shade in all of these places, it would take a long time, and what we'd eventually get is just this big shaded region underneath here. Right down there. The same idea as this. Like if we were to put dots at all the places where x is less than 5, we would wind up making that shaded region. If we were to put dots at every point where y is less than what you get when you plug in these certain x values into this equation, we would shade in all of that stuff. Okay. So together, this line and this shaded region represent all the values of y that are they equal to -2x minus 1?
No.
Less than, so, but is it also equal to? Yeah. It could be, if it's on the line or in the shaded region, then y will be either equal to, if it's on the line, or less than if it's below the line. Less than the value you would get when you plug in that corresponding x value. And just to contrast, what if y were greater than or equal to negative 2x minus 1? How would that look different?
Shaded top.
Shade above, yeah. All the values above the line would make y bigger than the y values on the line. Keep it in mind that how we get those y values is we plug in that x value. So if I plug in this x, I will get this y. Okay? And if I want to find y's that are bigger than that, look up here. If I want to find y's that are less than that, look down here. Have you guys ever done this before? Do you graph these inequalities?
Yeah.
Okay. You probably, I'm guessing, didn't look at it that way. Did you look at it that way?
No.
Was I right or wrong that you didn't look at it?
Like at first when you're just like drawing like a line down the middle, I didn't like I was just like, oh, I haven't really like thought about it, and then when you take a whole thing, like I say.
So so when I was all done, it's like, oh, okay, this is familiar. Okay. So keeping this in mind, we'll talk about another idea, but keeping this in mind about y's that are bigger and y's that are less than the y's on the line. I want you to do number 15. Remember that right? 15 and 2.8. Yep, that's the one. 15. Okay, so who's got this line, the line part of the graph, and how did you do it? Danica?
Well, I had to move the 2x to the other side first.
Okay, so just subtract the 2x on both sides. Why'd you do that?
Because it has to be y on one side and then all the other stuff on the other side.
All the other stuff. Okay, that sounds good. Okay, and this looks like mx plus b, right? That's a nice, convenient form to have it in. So I'll spare us all this. I think we all get. Then we're going to go up to a y-intercept of 6 and a slope down to over 1. If you have questions about what this line looks like right now, you think it should look differently somehow, just hold on to that question for a minute or two. All right. So again, let me say it again. If we pick a point from on the line, it's going to have an x and a y. Okay. And if I plug that x and that y into here, what's going to happen to both sides? If we pick a point from on the line, and you put that x and y in there, both sides will do what? They'll be what? Well, let's try it. How about this one? This one is, this point is 0, 6, right? If it's on the line. Okay, so the question is, what happens when we plug points that are on the line into this thing? What happens to both sides? Well, I put 0 in for x. Right? 0 times negative 2 is 0 plus 6. Okay, so this side is 6. And what do we plug in for y? 6. So what happened to both sides?
They're equal.
They're equal. That's the thing about this line, right? It's the line, this is the line, or the line that represents y equals negative 2x plus 6. Right? So any point on that line, if you plug it in to here, or here, right, both sides will be the same. Can both sides be the same? Up here? Why not?
Because
Like-
y has to be greater.
Y has to be greater? Y has to be less. Y is less.
So both sides.
And it doesn't have an equal to. So can both sides be equal? No, they can't. So can we take points from on the line and put them into this statement, this inequality? Not if we want the inequality to be true. Right? It'll make it false. It'll make both sides equal, and therefore one side would not be less than the other. Okay, so we're going to need to deal with that. But if y is less than this side, that's okay. So where would we find values of y that are less than the values on the line? Anywhere below, right? For this point, any point below it will have a y that's less than that y. Right? All those down there. And for this point right here, any point below it will have a y that's less, and so on for every point on the line. Okay, let's go back to the line. Can you pick points from on the line, plug them into the inequality, and have the inequality be true?
No.
No, it's false. Okay, just like this. Just like this guy right here, right? X couldn't be equal to 5, so he signified that with what? Circle. So we got to do the same kind of a thing over here. Like earlier, we had a similar kind of thing. Carl said, do nothing, and I said doing nothing is right, but then we have to make it more obvious that we do that we don't include this value. So the shading shows that all the points down here work. They all make the inequality a true inequality. But the points on the line don't work. So how can we show that we go up to the line, but we don't ever pick a point from on the line? A dotted line. If it's dotted, it's still there to guide us, to show us we can get close to that line, but there's also kind of an emptiness to it, where we know that it's a border, but we can't get to that border. We can't pick points on that line. If we were the best shaders in the world, and we could just shade in and not have a line, then that's what you can do, right? And not have that line there. But to signify that we're not going to include values on the line, we make it a dotted line. So here's the other idea. The way that you're typically told how to graph these, which I think it has some truth in it, but doesn't have like a whole truth in it. Say that we know this. Obviously, all of the shading, all of the points that are going to work are either going to be all down here, because they're all less, or they're all going to be up here, right? So if I hadn't shaded this yet, and I didn't know about the shade below or shade above based on whether y is less than or y is greater than, I would know that this side is going to be shaded or this side is going to be shaded. Right? What happens when I pick a point out of here and put it into the inequality?
It's true.
It's true. The inequality is true. This side truly is less than that side. What happens when I pick points from this region?
It's false.
It's false. Y would be greater than the stuff that you get over here. Okay? So points from here, true. Points from here, false. So if we didn't have anything shaded, we could just pick a point from one of those regions, from down here or up here, plug them in. If it's true, I must have picked a point from the shaded region. If it's false, I must have picked a point from the not shaded region. And if it's possible, if you want to do that, 0, 0 is a really nice point to pick. Okay? So we pick 0, 0, 0 for x, 0 for y, 0, right? This is 0, this is 0. And all we have on this side is 6, and then what we have on this side is 0. Is 0 less than 6?
Yeah.
It's true. So we must have picked a point from the shaded region, and we can just shade the rest of it in. And if it's false, you must have picked from the wrong side, and you can shade the other side. So you can test a point and shade based on that. But if we think of this above and below, I think it's a little more helpful as we look at different functions. Another function we could talk about is the absolute value function. Just look at an example. Y is greater than -2 times the absolute value of x minus 3 plus 4. This is just example number 5. Example number 5 and 2.8. We start out by graphing like the basic graph, the absolute value graph, which for the sake of time, move up 4, move to the right 3. That's our vertex. This negative means it's going to be upside down, it's going to open down. And this 2 means it's going to be twice as steep. So we'll come down to an over 1. And it opens down, and 2 and over 1. Just like that. If we were to pick points from on the graph, we plugged them in, both sides would be the same. They would be equal. Can both sides be equal? No, we don't have that condition. It doesn't allow for equality, only that y is greater than what you get on the right side. So we don't want to include that. And now we say, do we want y values that are greater than the y values on the graph, or do we want y values that are less? Greater, so the y values that are greater would be above this guy right here.